Hello everyone, this is Mohsen Saraj. I'm the Senior Application Engineer in Ansys working in Ozen Engineering. Today I want to talk about mesh adaptation and specifically about geometry-based mesh adaptation in parallel with the other criteria for the mesh adaptation in Ansys Fluent, for example, having boundary layer adaptation and also based on the gradient of the pressure. We have two videos on this topic. This is the first video. In the first part, I'm talking about the model and have to set up the mesh adaptation and compare the results with manual refinement. And in the second part, I have specifically showed you the workflow for geometry mesh adaptation and what are the tips and points to have successful application of this method. This is the workbench project. I start with from the geometry. As you can see, it is a simple geometry. It is a quarter of the pipe. Uh, Here we have sharp corners that it is important. If we look at from here, we have a step change in the cross section. If so, this is the structure, and if we check the name selections, one end is outlet and another end is inlet, so inlet to outlet. We have walls, faces, and this part, this is also wall, and walls, these are the walls, as you can see. And we have the size for periodic boundary condition that I will set it up in meshing. And also I added some name selections for assigning the local size in meshing that I'm going to use it for mesh refinement. For example, this part and this part, these are edges, as you can see, and side edges from other side. So this is the geometry for our how we can apply the geometry boundary condition here and compare the results with manual refinement. For the workflow, I have two paths for the workflow. This part, it is for I started with the geometry that I created by its default setup in Fluent, and then I have manual refinement for this part, and then apply the mesh adaptation techniques for boundary layer and based on the pressure gradient. One thing is that I have to also say this at the beginning. This problem involve checking the pressure drop between inlet to outlet. This is the way that I compare the performance of the mesh refinement, adaptive mesh refinement. Other path is this way, that I use a surface mesh. I use it for like an envelope to my domain, specifically to the walls and to the step change that I have the sharp corners for the geometry based mesh adaptation, and this is the here I set up the geometry based mesh adaptation. Let's start with Fluent meshing. This is the mesh. As you can see, this is no local sizing. I just choose the setup for the minimum and maximum sizes for the mesh. Set up the periodic boundary conditions on the sides of that. Okay, and describing the geometry, boundaries, I consider velocity inlet, pressure outlet, these two sides at periodic and shadow for the other side, and these are walls, that these faces and this part that you can see. Only fluid domain. For boundary layer, I just consider again default setup. For volume mesh, again just the default setup that I have. As you can see here, I have here the mesh quality for the orthogonality, minimum orthogonality. It is quite low, the default value, the default setup. This is something that you need to be sure about this. But here, fortunately, because we have the information here about the minimum orthogonality, which is it is 0.255. So the initial mesh that created by Fluent has a good quality, at least acceptable quality, based on minimum orthogonality that we have. So and number of cells is about 2586. So this is the mesh. Let's go for the setting of Fluent. I'm going to run it again. Just check the mesh quality. As you can see, it is 0.255, which is more than minimum acceptable orthogonality, which is 0.15. And number of cells, it is 2586. Let's also show the edges for the mesh. Inlet, outlet. This is the mesh for the outlet, and these are the insulation layers for boundary layer at the walls, and this is for inlet. As you can see, at the inlet I have 1 2 3 4 5 6 segment, and if you check the number of cells on this curved part of the domain, 1 2 3 4 5 6, only 6 part, 6 segment for the for that curve part of the domain. This is the boundary layer, as you can see here that we have it, and the bulk of flow has only 3 cells, which for sure is not adequate. It is not sufficient number of cells here. So we know that this mesh maybe not very optimum mesh, but this is what we have in Fluent, and see what's happened. Material, I set it up to water from the Fluent database library. Constant properties for density and viscosity. Boundary conditions. Inlet, it is velocity inlet. I just consider 1 meter per second for the velocity of water coming inside the domain. And outlet, this is pressure outlet, 0 for the gauge pressure. Operating conditions, The sides, side 1 and side 2, these are for the periodic boundary conditions, and these two parts for walls. So in this way we have a kind of modeling for the full cross section of the pipe. Also here I define two expression, one for the calculating the pressure drop between inlet and outlet, as you can see, and use it in the reports when monitoring the solution. And this is for and another one is for cell count. Okay, for the solutions, for the reports, I can use this part. One way to have the number of cell count here, I set it up this report because later when I use the mesh adaptation, uh, I'm going to see you that have the number of the meshes, the number of the cells changes and increased. This is one way to show the cell count, and also for the expression I can use here the dp the drop in the pressure. So these are my reports that I have it here for the domain, as you can see here. And for pressure drop, this is also the one that I use it, the difference between pressure of outlet respect to inlet. The setup for the solution, I didn't change anything here. Let's initialize the model. So now let's set it up for 500 iterations and run it. These are residuals, as you can see. This is the cell count. It is same, unchanged, because we don't have mesh adaptation, and almost constant magnitude for the pressure drop, 4500 and 45,157, this value. So this is for original mesh or initial mesh. We're done for the initial mesh. Let's move on to the refine mesh that are manually refine the mesh specifically here at the sharp corners that we have, and in this along this edge and this edge. So this edge, you can see that the length of the radius, it is 0.215 millimeter, and this one it is almost 3 times, almost. Let's look at the mesh. Opening the Fluent measure. As you can see here, I added a local size. This local size is for these edges all around that. I set the value for the segment. Each segment is local size is this value in millimeter. Update that, and also smaller sizes for the minimum maximum cell size for the surface mesh. You can see the size of the maximum cell size and minimum cell size compared to the domain dimensions. Okay, this is the surface mesh. 1 2 3 4 5 6 7 8 9 10. Now we have 10 segment and this curved part of the domain, and much more here, and also on the sides instead of only 3, 1 2 3 4 5 6. Much better than before, so it is more refined than before. Let's go for the next part, setting up the periodic boundary conditions and the rest of the steps, and perform the volume meshing. Boundary conditions, region, same setup for boundary layer at the walls, and for the volume mesh I added minimum, the constant of minimum 0.25 for the orthogonality. Generate the volume mesh. You can see much better than before. Before on this part of the domain we had 5 or 6 cells, now we have 9 or 10 cells. And we used to have only 30 cells, now we have 1 2 3 4 5 6 7 cells. Much better than before. So we know that on this part, because we have the smallest cross section, we should see the largest gradient for the velocity and for the pressure. And number of cells, it is almost doubled as before, and the minimum orthogonality it is 0.27, which is good. Let's move on to Fluent. Opening the Fluent with the manually refined mesh. Number of cells 5764 as we saw before. Mesh quality 0.2627, which is above 0.15, so it is acceptable quality regarding to the minimum orthogonality that we have. And look at the edges, inlet and outlet. We used to have 6 segments at the inlet, 1 2 3 4 5 6, same as before. But if you look at here at the sharp corner, we have much more, about 9 or 10 cells, and also on these two sides. So not only we have more cells on this curved part, also on this side for the bark fellow, which is good. I didn't change any of the setup, so let's move on to the initialization. Initialize the model and start running. 500 iterations. Residual cell count and okay, this value for the same number of the cells. And for the pressure drop, if I want to see how much is the pressure drop, one other way is that I come here and pressure drop and say that compute. You can see that 41,000, 42,000 compared to the 45,000 pascals that we saw before. So it is like about 10% difference in the calculation of the pressure drop between inlet and outlet. So you see that the mesh is really affect the our calculation. Now let's move on to the mesh adaptation. So far we have done for initial mesh and manual meshing. This one is about 2500 2600 cells, and the pressure drop is about above 45,000 between inlet and outlet. Refined mesh is about the cell numbers is about 6,000, less than 6,000 cells, and the pressure drop decreased to 21,000, above 21,000, so almost 10% decreased. Now we want to work with the original mesh, initial mesh, as you can see, okay, and see that how mesh adaptation can help us. Let's start this and see that how we can set up the mesh adaptation. So this is the initial mesh that we have, and one important point here is that minimum orthogonality quality, it is 0.2526, which is acceptable because it is above the minimum requirement of 0.15, okay, 0.15. So it is acceptable. The original mesh is acceptable. And if we remember about the number of cells at the inlet, uh, outlet and inlet, each about 5 or 6 cells at the boundaries for the inlet and outlet, and at the sharp corners also, I think 1 2 3 4 5 6. So just remember that, and at the bulk of the fellow only 30 cells, and these are the bonding layers that you're seeing that. So we have mesh adaptation based on two criteria. One, for to have more information layers into the boundary layer at the walls, and also to have mesh adaptation of the bulk of the flow, main flow stream, based on the pressure gradient, because we are working on the pressure drop between inlet and outlet. Let's start setting up the mesh adaptation. Either I can manually do it here or automatic mesh adaptation from the sidebar. For adapting the mesh in either way, I have a name for that based on the criteria that I use this predefined criteria for the applications, aerodynamics, combustion, multiphase, fellow. These are built-in criteria that created the criteria for the refinement and coarsening. Also, I can check it for automatic mesh adaptation. It is done per how many iterations, and this is the controllers, general controllers for that apply to all mesh adaptation that I have. I can use the register also to define the criteria for the refinement and coarsening. This is another way to do it. So one way is this. Another way is that in the domain on top, we have separate section for the adaptation. I can manually do this, and you see that we have similar uh, steps that we have to follow up to set up the mesh adaptation, and after that I can copy that to the automatic mesh adaptation if I want to have it to automatically done during the solution every, for example, 20 iterations or whatever. Let's start with cell register to define a criteria for the refinement. For boundary layer I use boundary, it is boundary, okay, and we need to know specifically to choose the boundary zones that these are only for walls. If I check the boundary layer, boundary conditions, You can see that these are walls, so I use this wall and also this wall, at least two number of the cells. And if I want to see the cells in this cell register, I can say that save and display. You can see that this is only like a shell the around the domain, and this is the walls, the wall zones, and it tell me that how many cells already registered and selected. Almost 1000 out of 2500 cells. So I already have one here that I can use it for mesh refinement and say that copy to mesh adaptation, automatic adaptation. It needs a name. I call it boundary. I have the criteria. I can say that every 50 iterations and say and click OK. So I have one criteria already set up for mesh adaptation. Let's work on another criteria, which is for pressure gradient. Because I already initialized the domain, I can see here field variable. But if you are seeing that this is gray out, so just initialize the domain and then you can use field variable. Here, for example, pressure, it could be velocity, it could be turbulence, the turbulence parameter, or other one. Here we want to perform the mesh adaptation for the refinement of the bulk of the flow based on the gradient of the pressure. Be sure to choose gradient, and what is, and give a name of pressure to this cell register. And it is good to know that what are the range for the maximum minimum of the pressure gradient. I can say that compute. You see that I'm just seeing 0, and the reason is that I haven't started the solution. Okay. So so one way is that I run this case without any mesh adaptation, similar to the way done before, for some iterations like a 10 or 20 iteration, and see that what is the range for the minimum maximum amount for the gradient of the pressure. Another way is the solution that we already have from the initial mesh and create cell register for pressure gradient and say that compute. Stand one for the minimum, above 7000 for the maximum, and average it is about 400. So there are different ways to set it up, this cell register. It could be just maximum, minimum, less than, more than, top value, low value, cell inside the range, outside the range. For example, inside more than 1, and say that, for example, 7000. We can see that here, save and display, almost everywhere. Almost all cells already marked for that. If I can say that minimum 100, you can see that how the numbers decrease, the number of cells, specifically about the pressure, about the corners that we are interested in, that this corner, this is a sharp corner that we have. So if we change it to 50, the minimum, okay, that's good, more than that, or maybe even 30. And decrease this to 5000. See, not too many changes in the number of the cells. 4000. Okay, 1000. Yeah, you can see it's now the before the sharp corners. We see that, okay, it couldn't be, it shouldn't be 1000 the maximum, say that 1500. Okay, I think between 30 to 2000 is good. Okay, or maybe 2500. Yeah, now we have even 30,000. Yeah, I think we're good. So this is from the initial mesh, and 2000, almost 2000, almost, so 2000 out of 2500. So back to mesh adaptation. Here we say that inside the range 30 up to 30,000 and save. Now we don't see any for this mesh register because we haven't started the solution. So if we go now to pressure gradient and say that copy, call the second mesh adaptation for pressure, use pressure gradient, and this one also every 50. Now go for general adaptation control. Two level of refinement is the minimum. This is 500,000 maximum cells, not bad. And this is also, we can here set the minimum orthogonality after mesh adaptation. We have it for now, just the default values. Solution reports, you remember that we had two. One, it is for cell count. We're going to use this and see that how the number of the cells increased, and this one as before for calculating the pressure drop between inlet and outlet. So we set it up the automatic mesh adaptation based on the boundaries and for the boundary layer, and also this one for pressure gradient. Also, before running, I am created a plane. It is x, it is a YZ plane. Okay, let's see where it is. Okay, I wanna have a plane right at the sharp corner, almost there. Yeah, I name it plane 7, create, and I check the mesh refinement at this section. We can see the mesh at this section right now. You can see that 1 2 3 on each side for the bulk of the fluid. 1 2 3 4 5 6 segment around this curved boundary, and 3 inflation layer. This is before the mesh adaptation starts. Okay, let's start the simulation. 500 iterations. Residuals, cell counts suddenly jump to 90,000 almost. cell count, another jump to 100 and almost 200,000 cells. The pressure drop almost constant. I'll back to you when this solution done. The solution completed. Residuals. Cell count is up to almost 200,000 cells, and the pressure drop is about 44,450 almost, and the cell count it is almost 205,000 cells. If we check the way that mesh count number of the cells changes, okay, we say that every 50 iterations at the very beginning it jump it from 2000 to 12,000, 10,000 difference, and then after 50 iterations from 12,000 to 94,000, and after 100 iterations from 95,000 to 201,000, and not much after that changing in the number of the cells. So if we want to have a comparison between what we got from manually refined mesh compared to the mesh adaptations, you can see that the initial mesh has about 2500 cells. Mesh refinement that I did it manually, it is almost double that, less than 6,000 cells, and the pressure drop from initial value of 45,000, above 45,000, it is decreased to 41,800, 900, which is about 7% decrease. But when I use mesh adaptation, that I'm using huge number of mesh cells compared to the initial mesh, almost 205,000 cells. Only I'm seeing that the pressure drop changes respect to the initial mesh only in less than 2%, in the cost of 100 times increase in the number of the cells. And this is because if I back and check the mesh quality right now, after the mesh adaptation, you can see that it is much lower than 0.01, which shows that it is not very good mesh. And if I also now check the mesh at the plane number 7 at the sharp corners, you can see that I have too many cells at this section, which shows that the mesh adaptation did already the refinement. For example, see how many more insulation layer I have at the walls, and also how many more cells for the mainstream of the flow. So it is good, but notice these bumps, these sharp corners at this outer boundary that I have. This is where I already showed you that I have 6 segments, 1 2 3 4 5 6 at the original mesh, and this one and this one, for example, these are initial nodes. So the way the mesh adaptation works is that it just will add more nodes in between the initial nodes, but does not change really or improve the curvature that I needed. You can also see the mesh here. These are original nodes, and these nodes added later by adaptation, mesh adaptation. Similarly here, you can see that. But you can see that we see bumps, okay, over these curved boundaries. That shows that the initial mesh is not good enough. And mesh refinement here, see, okay, not very good mesh adaptation happened here. So so although the initial mesh has good quality respect in base of the minimum orthogonality, if you remember that it is 0.26, which is above 0.15, but because I don't have enough segment for discretization of this curvature, that's why I see that I don't see much improvement in the calculation of the pressure drop, although I use 205,000 cells compared to the about 6,000 cells that I had in my manually refinement. So if you check the best practice guided in Ansys Fluent manual user manual, it is also mentioned that the initial mesh, okay, should really represent or can capture the physics of the problem. Here, for example, because I have these sharp corners and I'm interested in pressure drop, I need to be sure that the initial mesh can really show the uh, show the good performance regarding to the mesh regarding to the pressure gradient, specifically where I have high gradient. For example, here sharp corners that I expected to see much higher values for the gradient of the pressure and velocity. So I need enough initial nodes to capture some features geometrically, for example, this rounded shape that I have, and also physics of the problem. And based on that, I can use mesh refinement to improve the results. This is very important to note that otherwise the mesh refinement, a mesh adaptation can really worsen the mesh quality, right, that right now we are seeing here, and also does not necessarily gives a better calculation for the for here, for example, pressure drop less than 2% change compared to the initial value that I received from the original mesh. So what is the solution? Either we need to have good mesh to start, not only regarding to the minimum orthogonality, also to be sure that really we have good resolution to capture the geometrical features, for example, where I have the curvature, and also can also have the have the good representation for the for the fellow features here, for example, pressure drop. So look at the critical regions here, this sharp corners that I have. Be sure that you have enough nodes, enough cells there. Otherwise, what I'm saying that initial nodes are still here, and the mesh adaptation just add more nodes between them, but does not really change these contours. No. So one way is this, okay, that we have to be sure about that. Also, as you can see that right now along this curve, maybe I have tens of the segments. Okay, if you count these segments, you can see that. I don't need to have that such very high resolution. If I start, say for example, 8 or 10 segment at this cross, at this curvature, at this curved boundaries, and then based on that I can use another way of the mesh adaptation that we call it geometry based mesh adaptation, that we use it here by defining auxiliary geometry. I'm going to show you that in the second part of this video, how to set up this geometry based mesh adaptation, and based on that we can see that how we can improve our results. Please watch the second part of this video. Thank you very much.